Hello and welcome to online lecture number 19 for Chemistry 112 during the spring semester of 2020. In this lesson, we'll continue with chapter 21, which has been all about nuclear chemistry. And with this lesson, we hope to have a better understanding as to why some isotopes are radioactive, why some isotopes are unstable, whereas others are non-radioactive and stable. Nuclear reactions is only concerning the nucleus. So it's only concerning the protons and neutrons that compose the nucleus. When we have a nucleus, we have a very dense particle composed of either protons and neutrons. Of course, protons have a positive charge, neutrons have no charge, and there are two forces at work in the nucleus. You have the electrostatic repulsive force that occurs when you have two light charged particles near each other. So one proton will have electrostatic repulsive force against a neighboring proton, etc. The neutrons, because they have no charge, don't have any electrostatic repulsive force on each other or on the protons. But then you also have, so that electrostatic repulsion force is there to destabilize the nucleus. If that was all that's there, then you couldn't ever have more than one proton in the nucleus of the atom. Of course, we know we do. We have atoms with 100 or more protons in their nucleus. So there must be something else there that's there to stabilize the nucleus. And that other force is called the strong nuclear force. And this is just an attractive force that exists between any two nucleons, whether it's two neighboring neutrons, a neighboring neutron and a proton, or even two neighboring protons. They can also have this attractive force called the strong nuclear force, also called a nuclear glue. So it's this balance between the attractive forces, which will increase as the number of nucleons increase, versus the electrostatic repulsive forces, which increases as the number of protons specifically increases. And this strong force is especially effective over relatively short distances. Here's a survey of what are the isotopes that are stable, what are the isotopes that are unstable. What we find, kind of interesting, is that over 60% of all the isotopes that we know that are stable, that do not emit any radiation at all, they have both an even number of neutrons as well as an even number of protons. And the notes with even number of neutrons or even number of protons, that makes up another almost 37% or so. And only about 2% of all the stable isotopes that we know of have both an odd number of neutrons and an odd number of protons. So there's something special about having either an even number of protons or an even number of neutrons, or especially both, an even number of neutrons and an even number of protons. That's what we can learn just from observation. There's also, we can learn, is that there has to be some so-called magic numbers of protons or neutrons. So this is akin to our octet rule with understanding chemical reactivity, that atoms will gain, lose, or share electrons. Most atoms will do that in order to have exactly 8 valence electrons. With nuclear chemistry, these are the numbers, special magic numbers of either protons or neutrons that render that particular nucleus especially stable. And there are particularly stable isotopes that we know of that are so-called double magic, because they have both a magic number of protons and a magic number of neutrons. So two examples of that will be the helium-4 nucleus and the lead-208 nucleus. We can see with the helium-4 nucleus, helium-4 has obviously 2 protons, which is a magic number, and 4 minus 2 also gives it 2 neutrons. So it has both a magic number of protons and a magic number of neutrons. With lead-208, it has a magic number of protons, and 208 minus 82, 208 minus 82 is 126. So 126, notice, is also a magic number of neutrons. So these are expected to be and are observed to be especially stable isotopes. So these are observations, both the fact that if you have an even number, either neutrons or protons, or especially both, it's more likely to be stable, and especially if a particular isotope has either a magic number of protons or a magic number of neutrons, or especially both a magic number of protons and neutrons, those are expected to be particularly stable isotopes and not undergo any sort of nuclear reactivity or emitted radiation. So if we plotted all the stable isotopes, what we'll get is what's called the belt of stability. I think our textbook sometimes refers to it as the band of stability, or zone of stability, or valley of stability. But we'll call it the belt of stability, which is, if we plot all the known isotopes, and that's what's here in red, y-axis is number of neutrons, x-axis is number of protons. And what we find is that there's a pattern here, that there's a cluster of where those stable isotopes are and where they're not. And we can see that when the elements are relatively light, so less than approximately 20 for atomic number, less than approximately 20 protons, then that magic ratio between, that special, we'll call it special ratio between number of neutrons and protons is approximately 1. When you have moderate size isotopes, so the atomic number is somewhere between 50 and about 20, then that ratio increases to about 1.25 to 1 neutron-proton ratio. These are the stable ratios that are observed. And when we get particularly heavy isotopes, 50 to about 83 for the atomic number, the ratio has to be even greater, 1.5 to 1. Notice as the number of protons increase, so therefore the amount of electrostatic repulsive forces are increasing, we have to have, relatively speaking, more neutrons, therefore more that strong force there to counteract those additional electrostatic repulsive forces and still be stable. So these are kind of the special numbers, special ratios we want to kind of keep in mind that will help us predict whether a particular isotope will be stable or unstable. If it's a light isotope, you expect a ratio of 1 to 1 for neutrons, protons, a little bit heavier, 1.25 to 1 approximately, and the heavier ones about 1.5 to 1. Notice that this stops at atomic number 82. Atomic number 82 is lead, which indicates, and which is true, that there are no stable isotopes above atomic number of 82. So any particular isotope that does not have one of these special ratios, it's going to be unstable. We call these radioisotopes. These are isotopes that would, if we were to plot them, they would fall either to the left or right of this belt of stability. And because they're unstable, they want to become more stable. And so they emit radiation of one or more types in order to become more stable, in order for their ratio of neutrons, protons to get closer to this belt of stability. So we want to be able to predict whether a particular isotope is stable or unstable. And if it is unstable, predict what type of radiation it might emit in order to become more stable. So what we'll find is that if the neutron-proton ratio is too high, then we can predict that that particular isotope should undergo beta decay. It should emit a beta particle. So for example, carbon-14 is expected to emit a beta particle and become nitrogen-14. And we can see why that is the case. These are light elements. The atomic number is less than 20, so we expect a stable neutron-proton ratio to be about 1. For carbon-14, it has 14 minus 6, 8 neutrons, and it has 6 protons for a neutron-proton ratio of about 1.3, which is a lot higher than we expect it to be for a stable isotope. Whereas when it comes to nitrogen-14, nitrogen-14 has 7 neutrons and 7 protons for a neutron-proton ratio of exactly 1.0. And for these light elements, we'd expect that to be a much more stable ratio than it would be for carbon-14 with its 1.3 ratio. So carbon-14's ratio of neutrons, protons relative to what should be stable is too high. So in order to reduce that ratio, it emits a beta particle. Practically, as we saw in the last lesson, when a beta particle is emitted, a neutron becomes a proton, and therefore that reduces the numerator by 1, increases the denominator by 1, thereby reducing this ratio. If that neutron-proton ratio, though, is too low, then we expect positron emission. So example here would be boron 8 becomes beryllium 8. See why that's the case. We have boron 8 becomes beryllium 8 with the emission of a positron. These are still light elements, some of the lightest elements, so we expect a stable neutron-proton ratio to be approximately 1 at least. With boron 8, it has 3 neutrons to 5 protons for a neutron-proton ratio of about 0.6. Whereas beryllium 8, it has 4 neutrons, 4 protons for a ratio of 1.0. So if this ratio is too low, 0.6 is a lot less than we expect a stable ratio to be, it will emit a positron. By emitting a positron, a proton becomes a neutron, thereby the numerator of this ratio increases by 1, the denominator decreases by 1, so consequently the ratio increases. So these light elements, less than about 20, would expect a ratio of about 1. So that's one way we can always determine, predict what type of radiation the particular isotope may undergo based upon how its neutron-proton ratio is compared to a stable ratio. And that stable ratio does depend upon the atomic number, as we saw on the previous slide. As the atomic number increases, usually the stable ratio of neutrons, protons also has to increase. Alternatively, is we can also judge whether that ratio is too low, too high, based upon how the mass number of that isotope compares to the atomic mass of the element. Recall from Chemistry 1 that the atomic mass is the average mass of that particular element. It's a weighted average that takes into account all the different isotopes of that element, as well as their relative abundances. Well, the more stable isotopes are likely, because they are more stable, are likely to be more abundant naturally than the less stable ones. So as a result, then, the more stable isotopes will likely contribute more so to that atomic mass than the less stable isotopes. So specifically, what we can say is that if the mass number of a particular isotope is less than the atomic mass, that means the neutron-proton ratio is too low. And if that ratio is too low, we expect positron emission. Conversely, if the mass number is greater than the atomic mass, we expect the neutron-proton ratio is too high. As a result, we'd expect it to undergo beta decay. So for example, if we have molybdenum 102, the question is, what type of emission do we expect for this particular isotope? We want to determine for molybdenum 102 what type of radioactive particle it should emit to have a more stable neutron-proton ratio. So one way to do that is we can compare the mass number of the particular isotope to its atomic mass. This is just information from our periodic table. So we can see that our mass number, the 102, is greater than the atomic mass of this particular element, which is 95.95. Because the mass number is greater than the atomic mass, that means that the neutron-proton ratio is too high. And because the neutron-proton ratio is too high, we expect beta decay. We expect this particular isotope should emit a beta particle to become more stable. So that's one way to come to this conclusion. Alternatively, we can remember that for this size isotopes, a stable neutron-proton ratio is about 1.25. So we can, like we just saw in the previous example, we can calculate what that neutron-proton ratio is and then come to the same conclusions. So for molybdenum 102, it has 60 neutrons to 42 protons to give us a neutron-to-proton ratio of about 1.42. And 1.42 for this size isotope is a lot higher than what it should be. So neutron-proton ratio is so high, should undergo beta decay. And so if we wanted to write a balanced equation describing that, then we have molybdenum 102 would emit a beta particle, which remember is a potential electron. And then what's left, the missing particle here, then would also have a mass number of 102, but it would have an atomic number of 43 in order to show that the mass numbers are the same on both sides, as well as the total atomic numbers. And 43 means that it's going to be NB for niobium. In niobium, 10243, it has a neutron-proton ratio that should be lower. It should be much closer to a stable ratio. So we saw that for molybdenum 102, its ratio was 1.42, too high. For niobium 102, its ratio is going to be 59 neutrons for 43 protons. 59 divided by 43 gives us a ratio of 1.37. It's still higher than we expect, but we're moving closer to that belt of stability. We're getting closer to this ratio of about 1.25 for these size isotopes. So would it be surprising then if this isotope also then further undergoes radioactive decay to even get closer to this 1.25 neutron-proton ratio? These processes, these nuclear reactions, just like we saw with the chemical reactions, there's a rate to them that we can measure and we can express how fast these reactions are. And so that's what our next and last lesson will be all about, is the kinetics of these nuclear reactions.